This video covers section 3.5 on optimization for business, economic, and general applications. So our one objective for this section is to learn how to solve optimization problems using calculus. In other words, find maxes and mins of problems that apply to real life. All right, so here is our strategy. We're going to be utilizing all the tools that we've learned so far in the first 4 sections of this chapter to solve word problems, basically. All right, step 1, as always with any word problem, read the problem carefully. If relevant, make a drawing. Step 2, make a list of appropriate variables and constants, noting what varies, what stays fixed, and what units are used. Label the measurements on your drawing if one exists. Translate the problem to an equation involving a quantity, Q, that they're asking you to maximize or minimize. Then try to represent that quantity in terms of the variables that you've used from step 2. Step 4, try to express the quantity you're trying to maximize or minimize as a function of one variable. And then use the procedures developed in sections, this should say 3.1 through 3.3, to determine the max or min values and the points at which they occur. All right, so our first example. From a thin piece of cardboard, 8 inches by 8 inches, square corners are cut out so that the sides can be folded up to make a box. What dimensions will yield a box of maximum volume, and what is the maximum volume? All right, so let's make a drawing. So we have an 8 inch by 8 inch piece of cardboard. It's the original square here. You're going to cut out square corners. So each corner, if it's a square, has dimensions. We're going to use the variable x here. So x by x is going to be this corner. Same dimension over here, x by x. So an x by x square out of each corner. So if I cut along these lines, x and x right here, and take this off, same thing here, cut these lines and remove this corner, cut these lines and remove this corner, and cut these lines and remove this corner. These other 4 pieces can be folded up for the sides to create your box. So if we know that our dimensions are 8 all the way across, and we've pushed in here x and pushed in here x, this remaining line that's solid would be the entire width of 8, subtracting x twice, so 8 minus 2x. And then the other dimension of the other side of the box, once I remove x from each end, is also 8 minus 2x. So the base of the box is 8 minus 2x by 8 minus 2x. And then if you're folding up those flaps for the sides, your height of the box is that x, right? That's this side's going to push up to become your height. So if you have to read the problem more than once, you're going to draw a picture, start labeling it with what you know. So that is step number 1. All right, next we're going to write an equation for the volume, because notice back here they asked what dimensions will yield a box of maximum volumes. The quantity that we're asked to maximize or minimize is volume. So I need to recognize that from the question and write an equation to represent that quantity. So volume of a box is length times width times height. So from our diagram, the length and the width are both 8 minus 2x, and the height is x. So that's putting it in terms of the variable used in my diagram. All right, so here we're just going to FOIL this together, multiply that out, then distribute the x, and they rearrange terms a little bit here, but get my function that I'm trying to maximize in terms of one variable. All right, so from here we use the process we've talked about already so far in chapter 3. We want to find the max value of v, and this is what function it represents, so we can do that by using derivatives. So x must be between 0 and 4, because if our original piece of cardboard only had a width of 8 and I'm coming in x on each side, I can't come more than 4 inches, right? Because then they'd be right at the middle where you won't have any more space. And you have to take off some part of the edge so you can't have a negative value. So the x's that make sense, or the interval that we're looking at for that we're going to consider, are x values that are positive but up to the value 4. All right, so there's our first derivative. We're going to set it equal to 0. So here we just divided everything by 4. All those coefficients are divisible by 4 just to reduce the numbers. Factor it. Set each factor to 0. And solve. So we get 4/3 or 4. 4 won't really work because if you come in 4 units on each side, there's no space left to have a width. So that's why we have to consider what's reasonable. So 4/3 is the only critical value in that interval, because remember 4 we didn't include here. So now we need to find our second derivative. So we're going to have one critical value, so we can use that second principle from the last section. So our second derivative, 24x minus 64, plug in our critical value, 4/3, simplify, we get a negative number. So second derivative, negative, meaning concave down, and if it's concave down, that's the umbrella, which has a max. So the volume is maximized when 4/3 inches are cut away from each corner, and the maximum volume is whatever I get for the volume function that I wrote the equation for by plugging in that critical value. So that would simplify to 37 25/7 cubic inches. All right, so let's do another example like that. This time the sheet of cardboard is a regular sheet of paper, 8.5 by 11, typical size of a sheet of paper. This time they want to know, will the box hold 1 liter of liquid? So we'll have to do some conversions to answer that question. So 1 liter is 1,000 cubic centimeters, and our dimensions here are in inches, and we're given that 1 cubic inch is 16.8 cubic centimeters. So we'll use these conversions to convert our answer when we're finished. All right, so going off of example 1, if you visualize your rectangle that's 8.5 by 11, and you're cutting off the x on each end, so you'll have 8.5 by 11 minus 2x as one dimension, then the 11 minus 2x as the other, and then x as your height. So it's just the same as we did before, only before they were both 8 by 8. So it's just taking the entire length of each of those and subtracting off 2x in both, or subtracting off 2x altogether, meaning x in both directions. So our volume again is length times width times height. So 11 minus 2x, 8.5 minus 2x times x. Foil all that out and distribute the x. Gives me this. So both of these, so if I have 11 inches and I come in on each side x, I can't go more than 5.5. And if I had an 8.5 inch length, half of that is 4.25, so on the other side I can't come in more than 4.25, right? So in general, you've got to be between 0 and 4.25 because this is the smaller interval that's within. I can't use this one because 5.5 is too big for this. So this is my space that I'm looking at. So x is bigger than 4.25 won't work for that one shorter side, so we have to stay between 0 and 4.25 for our x value. All right, so our first derivative set to 0. Here it doesn't factor, partially because we have this decimal here. So we'll use the quadratic formula to solve this one. So negative b plus or minus the square root of b squared minus 4ac divided by 2a. So plugging in your 12, negative 78, and 93.5 for the a's, b's, and c's. Simplifying, you get 39 plus or minus the square root of 399 over 12. And that's completely cleaned up, I believe, which roughly is 4.917. The other answer, the 39 minus this, and then they did 31 plus. The other one was probably outside of the range. Oh, here they're showing the other one. So you get 4.917 and 1.585. So we'll pick the one that falls in your space. So remember our max value was 4.25. This one then is too big. So this is the only one. And since there's only one again, we can use our second derivative to check to see if it's a max or a min. So our second derivative with that number plugged in leads to a negative number again. So a negative second derivative means concave down, which is going to be a max. So the maximum at that x value. So the dimensions are approximately, this was x. If I plug x into the 11 minus 2x and the 8.5 minus 2x, we would get these results. So the total volume, length times width times height, or just plugging this into the volume function that we had established. Either way, we should get 66.15 cubic inches. The conversion they gave us at the beginning, converting that to centimeters, which would be this, 1,084 cubic centimeters. And that's greater than 1 liter. By the definition, the cubic centimeters, liter is 1,000, and that's bigger. So it has more space than that of a liter, so it could hold a liter of water. All right, here's another example. Example number 2. A stereo manufacturer determines that in order to sell X units of a new stereo, the price per unit in dollars must be P of X equals 1,000 minus X. The manufacturer also determines that the total cost of producing X units is given by the function C of X equals 3,000 plus 2X. A, find the total revenue, R of X. Find the total profit, P of X. Find how many units must the company produce in order to maximize their profit. And then what would the maximum profit be? So this is a very real life problem. Right? And also what price per unit must be charged in order to make the maximum profit. Okay, you can imagine why a company would need to know these things. All right, so revenue is the money you bring in. So the quantity you sell times the price you're selling it for. That's your revenue. So X is your quantity, P is the price. So they gave us the price function, 1,000 minus X. So this would be 1,000x minus x squared. That's total revenue function. Profit is the total revenue minus the cost, right? You have some costs involved, right? So the money you take in minus what you had to spend is the leftover is your profit. So R of X minus C of X. So we just calculated the R of X function. Subtract the cost function that we were given. So distributing the negative sign and cleaning that up, we get negative x squared plus 980x minus 3,000 for the profit function. All right, to maximize profit, we need to find the derivative. So the derivative of our profit function, set it to 0. Subtract 980, divide by negative 2, so 490 is our critical value. One critical value means you can use your second derivative to know if it's a max or a min. Second derivative of profit here would be negative 2. That's negative. Negative second derivative, concave down, that means max. Since second derivative is negative, the 490 yields a max. So profit is maximized when 490 units are produced and sold. And then the maximum profit that you would make if you sold 490 units is what you get if you plug that back into your profit function. So $237,100. So the stereo manufacturer makes a maximum profit of $237,100 when 490 units are sold and bought. Okay. The price per unit to achieve this maximum profit, take your price function, plug in the number of units, so 1,000 minus 490 would be $510 per unit. So if they can sell 490 at that price, they will maximize profit. All right, so we're going to repeat example 2 with a new price function and a new cost function. All right. So total revenue, you're going to take price per unit times how many units you sell. So price per unit is the P function times X units. So our X times our price function, 750X minus 2X squared. Total profit. We needed our revenue function, which we found. We were given the cost. So the profit is revenue minus cost. So revenue, subtract the given cost function, cleans up to be this. Then find the total number of units produced by using the first derivative. Right, we're trying to maximize profit, so that's the function we have to maximize. So first derivative would be negative 4x plus 1735. Set it to 0. Solve it for x, you get 433.75. Second derivative, since there's only one critical value, you can use your second derivative to see if it's a max or a min. Second derivative is negative 4. That's less than 0, meaning concave down, so that means you're getting a max at any critical value, so that would be around 434 units are sold. You need to round this to the nearest whole number for it to make sense. So then your maximum profit is the profit that you would get by plugging in that critical value. So 374,028. That's your max profit. And then the price per unit would be what you get if you plug that critical value into your price function. So the price per unit to achieve that is $882. All right, max profit occurs at the x values for which r prime equals c prime. And that's easy to see if you think about your profit function being p of x equals r of x minus c of x. So p prime equals r prime minus c prime. And if you set to 0, you could add the c prime over and get r prime equals c prime. All right, and it occurs when second derivative of r is less than the second derivative of cost. All right, example number 4. Promoters of international fundraising concerts must walk a fine line between profit and loss, especially when determining the price to charge for admission to closed-circuit TV showings in local theaters. By keeping records, a theater determines that at an admission price of $26, it averages about 1,000 people. For every drop in price of $1, it gains 50 customers. Each customer spends an average of $4 on concessions. What admission price should the theater charge in order to maximize total revenue? All right. All right, so admission price of $26, 1,000 people come in. For every $1 price drop, it gains 50 customers. All right. So we're going to let x be the number of dollars by which the price 26 should be decreased. Okay, if x turns out to be negative, it means it should be increased. Okay, so if x is how much it should be decreased, okay, our revenue total is going to be our revenue from ticket sales plus the revenue from the concessions. So the number of people times the price per ticket is the revenue from ticket sales. Number of people times $4 per person is how much they take in on average for concessions. It said customers average $4 on concessions. All right, so they bring in $1,000 if they sell at $26. But for every decrease, so the ticket price is going to go down, the number of dollars by which the price should be decreased. So if the price is now 26, it goes down by X dollars. That would be my new ticket price. It gains 50 people from starting off at having 1,000 people. If it were just 26, it gains 50 people. So you got to understand what we're letting X be to understand where this comes from. It said at $26 a ticket, it has about 1,000 people. They go down. For every $1 they decrease, they gain 50 people. Okay. All right, so the number of people becomes 1,000 plus 50x. So that goes here and here for number of people. Our ticket price is now 26 minus x, and our concession price is still 4. All right, so we're going to FOIL out the first binomial, the first two expressions, distribute the 4 here. Clean that up. You should get negative 50x squared plus 500x plus 30,000. So to maximize revenue, we're going to find its derivative and find the critical values. So there's the first derivative. set to 0. Subtract 500, divide by 100, you get 5. One critical value means you can use your second derivative to figure out if you have a max or a min. Second derivative is negative 100, that's a negative number. Thus, that critical value yields a max. When second derivative is negative, concave down means max, so the theater should charge. X was how much it should decrease the price by, so 26 subtract $5, so sell it at $25 a ticket, or $21 a ticket. Whoops. Sorry. So the original price they had, they need to decrease that by $5 to maximize their revenue. All right. Another example that is similar. A baseball team charges $30 a ticket and averages 20,000 people in attendance. Each person spends an average of $8 on concessions. For every drop of $1 in the ticket price, the attendance rises by 800 people. What ticket price should the team charge to maximize revenue? All right, so the revenue formula from the previous example. They average 20,000 people in attendance per game. X is going to be how much they should decrease the price by. So the number of people is going to be 20,000. They're going to increase by 800 people for every $1 drop in price. So if X is the number of dollars you're going to drop in price, 800 times that is how much you're going to gain onto the 20,000 people. Times price per ticket is now going to go down from 30 by X amount. So the number of people becomes 20,000 plus 800X times the price per ticket becomes 30 minus X plus the number of people again times how much they're spending on concessions, which was $8. Multiply out, distribute the 8, FOIL the first two, clean it up, gives you this revenue function. So you're going to maximize revenue by taking the first derivative, which would be this, setting it equal to 0, solving that for X, get 6.5. So this means that to make sure that there is a maximum, we need to use our second derivative. So second derivative would be negative 1600. No matter what, that's less than 0. Concave down means that we're getting a max. So substitute X back into your formula. So you had a $30 ticket. We should be subtracting or decreasing it by $6.50. So they should be charging $23.50 to maximize revenue. All right, so many real-life applications we wish to determine mins and maxes of functions using a modeling situation. All right, so we can utilize the stuff we have learned in Chapter 3 in order to do that. Identify a realistic interval for the domain. If it's a closed interval, endpoints should be considered as critical values. Maximum profit occurs at the x values for which r prime equals c prime and the second derivative of r is less than the second derivative of c, where r is total revenue and c is total cost when x units are produced. Basically, those examples are just coming up with the function that you're asked to maximize or minimize is the hard part, that you got to read through the problem and understand what's going on. But once you get to that, all the steps are the same as what we have done in the last few sections. All right, so that is the end of section 3.5.